Hello everyone, myself Ashit Desai, Assistant Professor, Mechanical Department. Today we are going to discuss here the unit first, that is basics. In that we contain first the properties of fluid. So first of all, we look at the learning objective for this session. So first learning objective is to know the importance of fluid mechanics. Second learning objective is to know the various properties of fluid mechanics. So after this session, some learning outcome is there. So first learning outcome is the student will able to the basic content of fluid mechanics. Second learning outcome is the student will able to explain about properties of fluid mechanics. So first of all, we look at the fluid properties. So in the last lecture, we have discussed density, specific weight, specific gravity, and specific volume. Now we discuss first, that is compressibility, second surface tension, third vapor pressure, fourth one is the capillarity, and last one is the cavitation. So first of all, we discuss here the compressibility and bulk modulus. So as we know that the bulk modulus is nothing but the ratio of compressive stress to the volumetric strain. So for the purpose, as we know that the piston is fitted with a cylinder, which is shown in figure. So when you're applying the pressure on a fluid, so that time increases the pressure, so automatically the volume will be changed. So here the pressure P is there, so when you increase it, we can take as a P plus dP, and for that purpose we have to know the volume. So when you press it or pressure it, then it should be changes, so that becomes V minus dV. So initial volume is V and final volume is V minus dV. So as like that, pressure also, P is the initial pressure and final pressure is P plus dP. So this is regarding the uh, that split cylinder. So first of all, that we'll discuss the formula regarding this. So this is the cylinder which is fitted with piston. So when you increase the pressure, that is dP. So dP is measured in terms of Newton per meter square, or you can say kgf per meter square. And while decreasing the volume, because when you pressing it or pressurize it, so it changes the volume. So initial volume and final volume. So decreasing the volume is dV. And volumetric strain. So volumetric strain means change in a volume divided by original volume. So change in volume is dV and original volume is V. So this is regarding the volumetric strain. So as we know that the this negative sign indicates that the volume will decreases with increasing the pressure. So this is regarding the negative sign. So as we know that the bulk modulus is nothing but an increase of pressure to the volumetric strain. So again I repeat here, the bulk modulus is nothing but, that is K is equal to increase of pressure divided by volumetric strain. So increase of pressure means dP. So we can place as a dP, that is increase in pressure, divided by volumetric strain. So volumetric strain is minus dV by V. So this is the ratio, and here we can take V on that numerator side. So that equation becomes minus dP by dP into V. So this is regarding the bulk modulus. So as you know that compressibility is nothing but reciprocal of bulk modulus. So that's why I can write as a compressibility is given by 1 by K. So this is regarding the compressibility and bulk modulus. Now next we discuss here the adhesion and cohesion. So for adhesion is nothing but it is a property of fluid which particles of different fluids which can be attracted. So here solid and mention that fluid. So when your solid and fluid is there, suppose example is glass and water. So water is adhere to the solid, so that is called as adhesion. So here two different media is there, one media is solid and second is a fluid. So this is called as adhesion phenomena, and this phenomena is happen, so that time the capillarity effect will be done. So here I mentioned that the capillarity is mainly due to adhesion. So whenever adhesion property is there, so capillarities happen. So this is the adhesion. So always remember that adhesion is between two different media, that is solid and fluid. So these two type of molecules will be attracted over here. So this is adhesion. Now next slide we will discuss here, that is cohesion. So In a cohesion, it is a property of fluid which can attract the same type of fluid will be there. So that means same media. So same molecule will be attracted over here. So this happens the surface tension. So surface tension is mainly due to cohesion. So again I repeat, the cohesion is in between same media, or can say same fluid. So same fluid will be attracted over there. So that is called as cohesion. And due to cohesion, the surface tension property will be there. So now we discuss first, that is the surface tension. So as we know that surface tension is nothing but it is a tensile force. So tensile force is acting on the free surface of liquid. So when free surface is liquid is there, when the liquid is contact with gases or is in between two immiscible liquids. So that time the surface tension will be happen. Surface tension means the tensile force is acting on a free surface. So this free surface is happen when it is contact with gas or that liquid, or you can say immiscible two liquids. So if you consider oil with water, so these are two immiscible liquids. So that time the surface tension phenomena is there. So this surface tension, or can say this that membrane will like under tension. So this is the definition for the surface tension. Now we move for the unit, that is SI unit is Newton per meter. So always remember that SI unit for the surface tension is Newton per meter. So here we have the three molecules. So in that content, uh, that A molecules, B molecules, and C molecules for a mass of liquid. So the molecules A, so here the molecules A will be attracted over the all the molecules. So this is the resultant force will be acted in a downwards, so that A is 0. So you can say the resultant force is acting 0. But molecule B is slightly is contact with free surface. So therefore it can be acted in upward as well as downward direction. So this not that net resultant force will be in a downward directions, right? Now the molecule C. The molecule C is contact with free surface. Free surface means it is contact with air. So liquid is contact with air, that is called as free surface, and therefore the it experiences the resultant will be in downward direction. So again I repeat, the resultant force for A is 0, the resultant force B is in downward direction, and resultant force C is also in downward direction. So this will cause a very thin film on a surface, so that will be acting as a tensile force. So this surface is called as a surface tension. So again I repeat, the surface tension is nothing but the tensile force is acting when the fluid, or can say liquid, is contact with the gases, or if it is two immiscible liquid is there. So this is called as a surface tension. So that membrane behaves a tension, under tension, that is called as surface tension. So unit is Newton per meter, and it is denoted by sigma. Sigma, that is sigma like this, and for mkms unit is mks, so that meter kilograms then second, that is unit is kgf per meter. So this is about surface tension. Now we see the examples for the surface tension. So first example is on a water, striders can walk on a water because of the surface tension. So this weight is less and it does not penetrate the surface. So this surface is behaving actually surface tension because of liquid is contact with gases. So that's why the striders walks on a surface of this water. Second example is floating needle. So here we can observe the surface tension. So sometimes this needle will be is an floating because of the it should be less dense, as well as because of surface tension phenomena. And if it is this surface tension breaks up because of some reasons, then needle will be sinks. So this is the effect of surface tension. Here also we observe the surface tension on a liquid droplets. So this liquid droplets is due to the forming of shape because of surface tension, and this is the shape is in the form of due to cohesive forces of the layer, so it can easily deform. So this is regarding the surface tension. So here we can observe the surface tension. So first is in a walk on a strader, so on the floor or that free surface, or you can say on a water surface. Second is a floating a needle. Then third is a surface tension and droplet. So here we can observe the effect of surface tension. Now we discuss the expression for surface tension on droplet. So the surface tension on droplet, so we have derived here. So first of all, we know that sigma is nothing but surface tension. So when it is happen that surface tension, whenever the two immiscible liquid is there or the liquid is contact with gases, so that time the surface tension phenomena is there, right? So P is nothing but pressure intensity inside the droplet. So here we consider a droplet and we have to divide two parts. So this is first half, and here this on a circumference it can behave a surface tension. So here we consider here, and D is the diameter and P is the intensity of pressure. So here on the surface of the droplets, it can behave the tension. So we have cut in two parts, I already mentioned, and then this is the one force which is acted, that is surface tension, that is called as tensile force, is acting on a circumference, and second force is nothing but a pressure force. So again I repeat, for droplet purpose we are divided two parts, and after that this on a circumference the tensile force will be acted, and for equilibrium conditions, or you can say for balancing of the forces, another upward another that force acts, that is called as pressure force. So first of all we look at for surface tension force. So this is the regarding diagram. For surface tension force is nothing but a sigma into pi d. So pi d is a circumference. So this is a tensile force acting due to the surface tension. Then pressure force. So pressure force is acting on the area. So that's why pressure force is nothing but P into A, right? Pressure force is equal to P into A. So P is the pressure into A. A is nothing but area. So area of this droplet is pi by 4 d square. Now these two forces we have to consider in equilibrium conditions. So that's why I can take a equal, because it is a in a opposite and equal. So that's why P pi by 4 d square is there on a left hand side, and right hand side P in sigma into pi d we can take as it is. And then we can, after solution, we take the example for that P is equal to sigma pi d, and that pi by 4 d square goes on denominator. So after cancellation of pi get cancelled out, then d single d cancelled out. So relation between this, there is the 4 sigma upon d. So 4 goes on upper side, so that's why 4 sigma and d at the denominator. So P is equal to 4 sigma upon d. This is the relation for on a droplet. So surface tension on droplet, the formula is P is equal to 4 sigma upon d. So here what it indicates, the pressure intensity increases with surface tension, and whenever the diameter increases, what will happen? Diameter increases, the intensity of pressure will decreases. So this is the regarding the surface tension on droplet. Now we'll discuss the expression for surface tension on hollow bubble, right? So lastly we discuss the surface tension on droplet. Now we discuss here surface tension of hollow bubble. So a hollow bubble means soap bubbles. So here also we can uh, take a two parts, but actually this bubble is in contact with an air for two times. So inside and also and outside also. Again I repeat, hollow bubble is have two surfaces is contact with air, right? So that's why it's subjected to the two forces again. So one is the pressure force and second is the tensile force. So as we know that tensile force is nothing but sigma into pi d, but it is we can take us twice. So it is we can take a twice because the soap bubble is has two surfaces contact with air. So that's why we can take a two times. So surface tension is nothing but 2 into sigma pi d, and here we can, on a right hand side, left hand side, we can write p into a, that is pi by 4 d square, and after cancellation we will get p is equal to 8 sigma upon d. So this is a relation for surface tension on hollow bubble. So this is the relation. So here also the diameter is depending, the diameter is increases, the pressure will be reduces. So this is the expression for hollow bubble. Now we move for surface tension on liquid Z. So liquid Z we have considered here, and we have to take two parts. So we can take half part, so that d is a diameter and l is a length. So here the pressure intensity inside this liquid jet have above the outside pressure. So inside pressure is maximum than outside pressure. So here we observe the forces on liquid jet. So first is a force due to pressure. So as we know that P into A is nothing but area of semi-jet. So that's divided into parts. That's why I can write semi-jet. So that semi-jet we can take as a P into area is nothing but length into diameter. So we can take PLD. Then for next, that is surface tension, we can take as a sigma into 2L, because we have to divide it into two parts, correct? So that's why I can take force due to sigma into 2 into 2 into L. Now we can take these two forces in equilibrium condition. So as we already taken for bubble, as well as that we can say that for droplets. So we can take these two forces in a equal and opposite direction, and after cancellation of this, the equation becomes P is equal to 2 sigma upon d. So this is related with the surface tension on liquid Z. So this is the formula for surface tension. So already we discussed. For water droplet, the relation between P and D is the P is equal to 4 sigma by d, and for soap bubble, the relation between P and sigma is P is equal to 8 sigma upon d. For liquid Z, the P is equal to 2 sigma by d. So this is regarding the surface tension. Now we move for the next phenomena, that is capillarity. So capillarity is defined as the phenomenon of rise and fall of liquid. So here observe that rise of liquid and here the fall of liquid. When it is happen? Because we have to take a small tube and which is in vertically placed over here, and this phenomena will called as a capillarity. So here rise of water is takes place, and here fall of liquid will takes place. So why it happens? Because of attraction between the wall of tube and liquid molecules. So in case of water, so here example is there. In case of water, water is added on a glass tube. So that's why the attraction between the solid and fluid is there. So that phenomena is called as adhesion. So due to adhesion, the capillarity happens. Capillarity means again the phenomena is rise of liquid, right? So here the adhesion bonding is more as compared to cohesion. So that is the case. That's why the capillary rise will be happen. So this is regarding the water. So if you place a mercury, so what will happen? So when you place that vertical tube, so therefore the attraction between this fluid and solid is less. So that means what? The cohesion bonding is maximum than adhesion bonding. So that's why here the rise, it will not happen, only that capillary fall will happen. So here we can observe that surface tension for capillary rise and capillary fall. This is convex shape, this is convex shape and concave shape. So here also called as meniscus. So meniscus means curvature part we can observe here. So this is related with capillarity. So again I repeat, the rise and fall of liquid when only we can place that tube, that is capillary tube, the which is related to the adjacent layer of liquid, and here observe the phenomena, that is rise and fall. So rise and fall is happen due to because of the bonding between that fluids. So here adhesion bonding is maximum, then in that case capillary rise will be there, and The cohesion bonding is more that time that capillary fall is there. So this effect is called as convex and this effect is called as concave. So in capillarity is expressed in terms of centimeter or you can say of liquid. So this is regarding the capillarity. So here we observe the effect. So this angle is acute angle theta. So in case of water, this should be 0, as if it is fresh water and it's that and then angle is taken, so that convex angle is 0, almost 0. And if it is mercury or any other liquid is there, so that time if case that obtuse angle, so I can say obtuse angle is there, so that is angle theta. So this is regarding the concave shape, that is Vinicius or can say concave shape, here called as a convex shape. This is angle of contact. So here we can see the examples or can say we observe the capillary actions over here. So first is liquid rising inside a straw, so that is called as capillary action, that is capillary rise. Paper towel absorbing water, so this is the absorbing water, that is nothing but capillary action. Plant roots absorbing water, so plant the absorbing water, that is nothing but capillary action. Sponge or can say sponge, so that time water can be absorbed here. Tissue papers for absorbing the links, so here tissue paper is there and we can placing ink, so that capillary action will take place. The next is draw inks to the tip of foundation pen nibs, so here also capillary action is there. So in that examples we observe the capillary effect. Now we move for expression for capillary rise. So in that case, first of all, we know that the capillary rise means we can place the vertical tube which is adjacent to the layer of fluid and which is in vertical manner. So in that case, if it is liquid we rises, that is called as capillary rise. So here sigma is nothing but the surface tension, then h is the height of the tube, so height of the liquid level, so you can say height of the capillary rise, and theta is the angle of contact. So previously I mentioned that theta. So this theta is in a capillary rise, it is acute angle. So it is acute angle. So as we know that the weight of the fluid is equal to, so actually the capillary rise when it is takes place because of weight of the fluid. So as we know that the weight of the fluid is equal to volume of the fluid into specific weight, right? So volume of the fluid means that area of tube into this height. So area of the tube. So we can take area of the tube over here and the specific weight. So specific weight is equal to rho into g. So I can write specific weight is nothing but rho into g. So that's why area of tube is nothing but pi by 4 d square. So we can take area for the tube pi by 4 d square into this h, because height is takes place, into g. So into rho into g. This is because of specific weight. Okay. So the formula for that, the for equation becomes pi by 4 d square h into rho into g. So this is equation number 1. So again I repeat, so this effect it causes because of weight of the fluid. So that's why weight of the fluid is nothing but specific weight into volume, specific weight into volume, specific weight into volume. I can write here. So again I repeat, specific, actually this capillary rise is depend on first phenomena, that is that weight of the fluid. So weight of the fluid we can calculate from specific weight is equal to weight of the fluid divided by volume of the fluid. So we can take on that side what will happen, weight of the fluid is equal to volume of fluid into specific weight. So as you know that specific weight is nothing but rho into g. So that's why I can write here, instead of volume, the area into height. Volume is nothing but area into height. So height is this, that is h, and area, that is pi by 4 d square h. So pi by 4 d square into h. Specific weight is nothing but rho into g. So these are two formulas for specific weight. One is the weight upon volume and another is a W is equal to rho into g. So this is the phenomena. And second, for the vertical component, so this is about the surface that contact with the tensile force, so that becomes sigma into pi d. So actually I had discussed with the effect of the surface tension, so we can take sigma into pi d but into cos of theta, because this component is try to compile for a horizontal. So in a horizontal we can take cos of theta, so that's why we can take cos of theta over here, because it resolves two components, cos of theta and sin of theta, but we have take a cos of theta because it can tends to 0 1. If the fresh water is there, or I can say clean water is there, that time the theta will 0, that means this angle, or I can say acute angle, will be 0. So that's why the sigma count, it can be traced to that horizontal directions. So that's why we can take cos of theta. So again I repeat, for this capillary rise effect is depending on that weight of the fluid and tensile force, and we are computed for equation 1 and 2, and under the equilibrium conditions we can take a pi by 4 d square into h into rho into g is equal to sigma pi d into cos of theta, like this. Pi by 4 d square into h into rho into g and is equal to sigma pi d cos theta. And after that we required into capillary rise, that's why h. So we can uh, simplifying the terms, so we can take the h is equal to rho into g, we can take on that side pi by 4 d square and sigma pi d cos of theta. So after solution we will get equation. So here the cancellation will terms will there, pi will be cancelled, 1d cancel, 4 goes upward side, so that's why 4 sigma cos of theta and rho gd, so rho gd. So that's why the capillary rise equation becomes h is equal to 4 sigma cos of theta divided by rho into gd. So here sigma 4 and 4 is the constant, sigma is the surface tension, cos of theta, so theta is the angle between the this tube and this concave shape, that's why convex shape, so that is theta. And rho is nothing but density of the fluid, so if it is density of water where there mercury is there, so you can according to take this rho. G is 9.81 and d is the diameter of pipe, or can say tube, diameter of tube. So this capillary tube is having 2 mm dia, 2 mm dia. So when you're placing it, then it should be affected, otherwise if you increase the diameter it should not happen, this phenomena. So this is called as capillary rise effect. So for next, that theta is for water and clean gas. So clean glass tube is almost 0, so approximately 0. Hence cos theta is unity, because when you put the cos theta, theta will equal 0. So cos 0 is nothing but 1. So you can write for equation is h is equal to 4 sigma rho gd. 4 sigma rho gd for capillary rise, or you can say for water. So clean water is required, right? Or you can say that clean glass tube is also required, right? So this is regarding the capillary rise. Now we will discuss same for capillary fall. So same effect will be there, but this convex shape is there. Instead of that, concave shape is there in a capillary fall. So next effect, that is capillary fall. So capillary fall will be there. So that theta is the angle of contact. So it is in between the curvature with our vertical tube, that is nothing but theta, and that height is nothing but h, correct? So this is h is nothing but height of depression. And here the two acting forces is there, one is a weight of the fluid and another is the that hydrostatic force, that is nothing but that surface tension force. So again I repeat, there are two forces will be acting, one is the weight of the fluid and another is the surface tension force. So last time we discussed this same phenomena for capillary rise. So sigma is the surface tension, theta is the angle of contact. Similarly, we know that the weight of the fluid is responsible for this effect. So we can take weight of the fluid is equal to specific weight into volume of the fluid, or can say volume of the fluid into specific weight. Only weight of the fluid is equal to on that side and volume into specific weight. Why we can take this? Because of we consider here weight of the liquid, because this phenomena is depending on two parameter. One is the weight of liquid and another is surface tension. So for simplification, weight of liquid is equal to specific weight into volume of liquid. So volume of liquid means area into height. So area is pi over 4 d square and height, that height is small h, and into specific weight. So specific weight, another formula is rho into g, right? So you can place rho into g over here, and instead of volume I can write area into height. So area into height, area into height, rho into g. So instead of area, pi over 4 d square h rho g. So this is equation number 1. Similarly for equation 2 is nothing but surface tension. So surface tension is nothing but sigma pi d for cos of theta. So sigma pi d cos of theta. So here curvature effect is there, and this theta is angle, so that's why we can take a theta cos over here. So equation becomes sigma pi d cos theta. So equation 1 and 2 we can equate with. So after equating, so that solution will be, the equation becomes same, that is h equal to 4 sigma cos theta divided by rho gd. So same formula is there for capillary rise and capillary fall, only this diagram is changed. So according to change we can modify it. So again I repeat, the capillary rise and capillary fall, the effect will be done in that two forces will be considered here. One is the weight of the fluid and the second one is a surface tension force. So after these two forces equating, we'll get equation. So that equation is h equal to 4 sigma cos theta rho gd. And for mercury, the theta is 128 degree, right? So 128 degree for theta. So this is the formula for capillarity. So h is equal to 4 sigma cos theta rho gd. Here h is the capillary rise or capillary fall, sigma is the surface tension, theta is the angle of contact, rho, that is the rho here. This rho is called as density, g is 9.81, and d is the diameter of tube. So here I mention again that theta for water is 0 and theta for mercury is about 128 degree. So this is regarding the capillary effect. So application of capillarity. So when you observe this phenomena, actually lubricating oil spread easily on all the parts because of their low surface tension. So this is effect of surface tension. And now we have to know the effect of the dirt particles with surface tension. So again, this is the for surface tension effect. Okay. Now next we move for vapor pressure. So vapor pressure, when it is called as a, when the temperature increases, so what will happen after increasing the temperature, so that it should be boils and vapor will be forms in a closed container, and this causes the liquid gains the kinetic energy to the molecules and it overcome the intermolecular forces of attraction, and that should be converted to liquid phase, liquid to the vapor phase, and that vapor will be acting a pressure on that container, that is called as vapor pressure. So vapor pressure increases with increasing the temperature. So this is called as vapor pressure phenomena. Now next phenomena is for cavitation. So cavitation is a phenomena of formation of vapor bubbles. So here the formation of vapor bubbles in a that region where the pressure falls below the vapor pressure. So vapor pressure will falls over here, and here the sudden causes of that bubbles, that vapor bubbles will be collapses in that region. So in therefore this is the region of vapor pressure. So it causes the that effect of pitting action, or can say it can substitute to higher pressure, and therefore the metallic surface will be that cavitate, or can say it can wear out. So here the effect of cavitation you can see easily, that's why it is, the effect is called as cavitation. So again I repeat, the formation of vapor bubbles of a flowing fluid in the region where pressure of liquid falls. So where the pressure will be less, at that time the vapor bubbles will be formed and it can collapses at higher pressure regions. So that causes effect that causes effect that is nothing but cavitation. So that cavitation effect that corrodes or can say wear out the metallic parts. So here we observe the effect of the cavitation. So this is the uh, that wear out, as well as it can create a sound or can say noise into the uh, that pipe or can say in the tube, as well as it can reduce the efficiency of this that pump or you can say impellers. Then it can flowing condition of undesirable. So this is by this effect is reduced by there are two methods. While increasing the external pressure, if you increase the pressure, external pressure increases, so that effect will be minimizes, as well as we can decreasing the vapor pressure. So if you decrease the vapor pressure, automatically this cavitation effect will be negligible. So this is the regarding the effect of cavitation. So here we are discussed different points related with this. Uh, so first of all, we discuss the bulk modulus and the compressibility. Second point, we have discussed the adhesion, cohesion, and on that basis, we discuss all the surface tension phenomena. And that basis, we discuss also capillary actions, then examples of the that capillary effect as well as surface tension effect. And lastly, we discuss the vapor pressure and cavitation. So in the next lecture, we will discuss the numericals on surface tension and that capillary effect. Thank you.